Rene, I am, well, as you are the first speaker, just to, I am the director of the Institute, and I am here only to say hello, and I will also sit in the room for a while. Welcome to this course in neutron stars. I would like to start thanking the people that took the time to organize the course, for organizing it, so for taking this time. This is part of the academic training program of the Institute, and this academic training program is both for PhD students and postdocs, but also for the junior and senior staff of the Institute. So this is basically for the whole Institute. And the idea is that we organize some courses that could be of some general interest. And in particular, those courses which may find some links between different programs, different activities at the Institute. So I think the very first one was the one on gravitational waves we organized a couple of years ago. And this one in neutron stars is a very clear, was a very clear candidate. So the topic was a very clear candidate for having such a course in the academic training network, academic training program, sorry. Because the neutron stars are objects that link together several different physics, from nuclear physics to astroparticle physics, gravitational waves, or QCD. So there are several groups in our institute working in related topics, and with this, and in particular also in neutron stars. So with this course, this is a first step also to enlarge the communication between these different groups. So I stop here. So Rene, thanks for accepting lecturing in the course. And well, I wish all of you a nice lecture course. Thank you very much. So if you are ready, I mean, and now Christoph will take.
Maybe no, Thomas will take the chair.
Oh, yes. Thomas will take the chair.
Oh. Can you hear me, or should I get closer? Yes. Okay. So, well, I asked whether he could hear me. I guess so. Right. So then we have like two hours of lecture scheduled. So I think it would probably be good to have a short break, let's say about halfway. So if you want to structure things so that we don't have to have a break exactly at halfway, but if you find like a place roughly halfway through what you have to present, then we can take maybe 5 minutes for questions, and then 5 minutes break to stand up, wake up, get some fresh air. I think that would work. So otherwise, I don't know if I should introduce Rene. He's maybe works in Manchester at the Jodrell, I think the Jodrell Bank Observatory, which is one of the first big radio telescopes to make a lot of pulsar observations, well, pulsar neutron stars. And he's been working on neutron stars for a long time. So that's all I can say in detail, but he's agreed to give this general introduction. So if you're able to share the screen, I guess please take it away.
Yeah, okay, it's working now. Thanks very much for the introduction and also inviting me. Obviously, it's a pity I'm not here in person with you. I really wish I can visit you folks eventually. I'm sure that we'll get there. So yes, so you can see my screen share, yeah? All good? Okay.
Yeah, yes.
Okay, very good. And I'll just So I'll just get the chat window in the corner, just in case somebody online or there's anything that happens. All right, so I was asked to give this this introduction to neutron stars and pulsars, and I must say it's quite a daunting task because there is so much to say. So I'll try and do my best to cover a broad range of areas. And strangely enough, despite the fact that I've worked on the topic for now something like 15 years, I never given like a, except for public talks, like a really sort of like basic introduction, from sort of start to end. So there was actually a lot of areas where, I really had to investigate. So that was quite pleasant actually while preparing my talk. So here's the, I can change slide. Yeah, so here's the overall content of my presentation. So I'll be talking a bit about the history of neutron stars and pulsars. In my talk, I'll use them quite interchangeably. So if I, sometimes I really mean pulsars, but in general, pulsars, obviously, which are a flavor of neutron stars. So a lot of the physics, obviously applies to both. And I'll go over some of the discoveries and key moments. And also, I'll take you through some of the basics of the neutron star and pulsar model and the lighthouse model for pulsars. And I'll also, mostly in the second hour, I'll look at the using pulsars as laboratories, because there's such extreme objects that we can use them to essentially probe physics in a way that we are otherwise unable to do so on Earth. I've picked this nice little image of the Crab nebula seen at various wavelengths because I think it's quite representative of the study of neutron stars and pulsars, which is really across the entire electromagnetic spectrum, and even nowadays is obviously in the non-photon messengers, such as the gravitational waves with LIGO, but also we're still in early days, but eventually even with neutrinos. And I'm mostly an observer slash person that does like numerical modeling. So in my presentation, I'll focus a lot on the observational aspects, but I think during this course this week you'll have a lot about the theoretical side. So I thought a good theorist always knows where the data comes from that they base their theory on. So hopefully that's going to give you the sort of the big overview. So the first section is about the early days of neutron star science. So I won't go on with every single date of neutron star science, but I think the few keys are on this slide. So the neutron was discovered by Chadwick. Chadwick was actually born not far from Manchester, and he actually studied at Manchester in his early days under Rutherford. And funny fact, he went to study in Germany. He wanted to do his PhD in Germany, working with, I believe it was Otto Hahn. And then the First World War broke, and he got imprisoned immediately with a bunch of other international scientists. So it was basically an imprisoned camp for the entire war, and was released only on the armistice. And he would actually ask for various bits and bobs so that he could do science in his prison with other people. And they had like a science club. And he even found a type of toothpaste that was actually slightly radioactive. And he did some experiments during the war on that. So when he came back to England, he then went to Cambridge to do his PhD, studying again with Rutherford, who had then moved to Cambridge. And that's where he started studying what led to neutrons about 10 years later. So Rutherford had speculated that neutrons might exist, but he thought there would be more like essentially a mixture of like proton and electrons that would kind of bound together and would act as a neutral particle in atoms. Because after Rutherford's discovery of the proton and the nucleus, basically, it was clear that nuclei were heavier than the number of, that the charge that they carried. So it was clear that there were more than the number of neutrons, that you could count from the charge in a nucleus. and therefore they had to be something else that was electrically neutral. So, and then eventually Chadwick, made his discovery, and that's essentially the device that was used for the discovery. So I won't extend too much on that, but the neutron was discovered in 1932, and then I'll skip over that and come back. But 2 years later, Bade and Zwicky essentially coined the term supernova in 2 papers. So they had 2 papers that year, and really insightful papers. So in there, they basically hypothesized that neutron stars could form from exploding stars at the end of their lives, what they termed supernova. And at the time, novae, which are like basically white dwarfs that experience nuclear thermonuclear outbursts every so often as they accrete, which we call now novae, and supernovae, people would mix them all, in the same category. But then it was becoming clear that there were different origins and some subcategories. So they recognized that some of these explosions would be from massive stars exploding at the end of their lives, and they could shrink down to very small size and have huge densities. In the same paper, they also connected them to cosmic rays. So they figured that they could be charged particles accelerated by the huge magnetic fields, and that could produce cosmic rays. And also, their quantitative details were not very strong, and some were wrong or missing. But overall, the gist, was there to pose basically the existence of neutron stars. And then the same year, and then and through a couple of papers, Tolman, and then also Oppenheimer and Volkov in the late 30s, basically put together the general relativistic solution to the stellar structure of a neutron star, but also of essentially most stars and compact objects. So these sort of 2 groups or set of papers really laid the foundation for the theoretical knowledge of neutron stars that we have today. And I'll get back to that later in my presentation. But something that was discovered a bit later is that Landau actually calculated what is sometimes coined a super neutron atom. So basically, he was already a brilliant quantum physicist, and he was working with the model of nuclei. And then basically he just thought for himself, well, what if my nucleus, instead of having a couple of hadrons, the nucleus would be like a sort of macroscopic scale nucleus, maybe even the size of a star. And so he just constructed this sort of theoretical nucleus out of neutrons. And this was basically a neutron star. So for those of you who might have done during your undergraduates a nuclear physics course, using for instance, the liquid drop model. So you can essentially build a model for atoms out of semi-empirical laws, that are attractive and repulsive and symmetry exchange and the likes. And you can, in principle, there's no limit to how big you can make it. So that was more or less, Landau's idea. But if I recall, I mean, being from Eastern Europe, I think some of his publications were missed, and that's why people only found out later, if I recall correctly. Okay, so then people did carry on the work on nuclear physics and particle physics, but on the theory things progress a little bit. But obviously, at some point for theory to really make big leaps, you also need observational progress, and that's what happened in the mid 60s. So Martin Ryle had already basically developed the concept of radio interferometer, which is the idea of connecting together a bunch of radio antennae so that you can actually form an image, for instance, or get an instrument that's more powerful, that's more sensitive than just the individual components. And UH was also fundamental to the early days of interferometry, which the Nobel Prize that Ryle and UH got was in big part for the interferometry and also the discovery of pulsars, as we will see in a minute. So in '66, UH started building a new radio telescope in Cambridge for the study of interplanetary scintillation. So basically, distant galaxies, they appear essentially as point sources. And as their light propagates through the solar system, because there's, the solar wind, so there's ionized medium, between planets, and this essentially makes the light from distant galaxies, twinkle, so especially quasars. And it basically is the same principle why stars, twinkle at night, especially when they're low at the horizon. And so by studying the scintillation of distant galaxies, they could, for instance, get, probe the solar system, but also interstellar medium. But also they could try and measure things like the size of these objects. So UH needed help for his interferometer. We see it fully built. So that it's basically a bunch of wires, and it's basically like a giant, car or home radio dipole, and they're all connected together basically. So so UH needed help, and he recruited a bunch of students to help him. One of them was Jocelyn Bell. So she was just a starting PhD student basically when the dish was built. And she helped building it, but also, her PhD project was supposed to be on the interplanetary scintillation. So she joined the team, and then she was assigned to, start collecting data. So obviously there were no computers, so it's just, essentially a chart recorder, a bit like you see like the old seismograph, right, with a pen chart, and then it just like moves according to the voltage that's detected to the telescope. And basically, it produces 30 meters of pages, with graph on it. So she had to go through all of that basically every day, or other students, working on the project as well, to look at the signal and see, what was there. The telescope is not steerable, right, on the previous picture, so it's always pointing in the same direction. So, but they can phase the array by giving different lengths of cable to form essentially a coherent addition of the antenna pattern. And this way they would basically always point towards like the same direction, which I believe was due south, but then they could phase the array so that the antenna system was more or less sensitive at different elevation, local elevation. So this way they could essentially every day get a scan of the sky in some range of declination, basically. And then as the object transits, it would be visible for a couple of minutes in the field of view, and then they could essentially get the rough position of the object and then do a survey for various, radio sources. So on August 6, '67, Jocelyn found this weird scruff in her data. So this is like an example of like one of these recordings. So it looks mostly like noise. You can see here, like she labeled it interference. Interference would tend to be essentially like positive and negative kind of noise. So they go in both directions. But then you can see at some point that there's like this other pattern. And obviously, even to me, like it all looks a bit the same, but basically she recognized that this little scruff was not the regular type of interference that she would tend to measure, like this one next to it. So a lot of the interference back in the days was, already human in origin. For instance, the spark plugs in cars back in the days were infamous to produce a lot of radio interference, and so were the light switches, in houses and buildings. So this one was different. And further inspection of her data revealed that actually she, later on, she found other such scruff at the same position in the sky. And that's quite key. It was the same position in the sky, but the source, whenever it would come back with a delay that was 4 minutes earlier every day, basically. So it meant that it was at the same fixed location with the stars, because our standard day is 24 hours, but the sidereal day, right, the day according to the stars, is 4 minutes shorter because the Earth spins, but also it rotates around the sun. So the stars are on a 23 hours, 56-minute cycle. So yeah, so the object was fixed in the sky, and then it took a couple months. Basically, it took until the end of November for like the first, pulsar observation on a high-speed recording to be made. And the thing is, essentially, if you would tweak the gains of the analog system, and then you would put a recording chart that was faster, you could basically get more time resolution. Okay, the thing is, they could not leave that system on. Just like today, our hard drives have a limited, storage space. Back in the days, it was basically, the feed of paper, to the recording chart. You could just not leave it, record at super high speed because the stack of paper to analyze would just be ridiculous. So she basically had to get up, like really, in November, essentially 19 hours is basically probably somewhere, in the late afternoon or so. And then so she had to get up, but then as the year went on, she had to get up at various times of the day or get to the observatory at various times of the day to basically switch the recording system just a couple minutes, before that CP1919 source was to transit so that she could, get the high-speed recording. And on this one, you can clearly see the pulsations of the source, and they're every 1.3 seconds. And it was a very challenging observation because it turns out that CP1919 is we know now it's a pulsar, but it produces giant pulses, and also it tends to scintillate quite a lot. And on a lot of the previous attempts she made, the pulsar was not visible. Basically, there was always, the pulsar was always very faint. And then on that particular day, like she ended up being able to, get a proper recording. And so then pulsations, that was really remarkable and completely unexpected. Initially, they nicknamed the source LGM, Little Green Man, #1, because, like the Sputnik, right, that had been launched like just about a decade earlier, and the Sputnik was, basically just like a beeping, probe. So the source they had just discovered was, sort of reminiscent of it, but they knew that it was sort of, beyond the Earth because of the fact that it was synchronized with the sidereal time, unless somebody had figured out a way to make a source like stand at the same location compared to the stars. So then before Christmas, she found another 2 of these sources. So aliens, were everywhere, but obviously they didn't really believe that was the case. So then they started working on a paper, a really remarkable paper, and I'll go in a few details now. So that was the famous Hewish et al. Paper from February '68. So the first pulsar paper. So there's a bit of text here about, I'm just going to summarize basically the main content of the paper. By the way, it's a lovely read. It's about 4 pages long or so. So it's not, it's not very long. So the first thing is, the pulsar is pulsating, the source was pulsating. So they measured the pulsations at different times. And then they concluded that the pulsations were, the source was intrinsically constant to better than 1 part in 10 to the 7. Okay, so that's pretty amazing, and it's kind of illustrated in the chart that's here. So if you have a pulsating source, you expect that the period will change throughout like the day and the year, even if it's intrinsically the same period. And that's because the Earth rotates, and that's also because the Earth orbits around the sun. So therefore, there'll be a Doppler shift just due to the fact that we're not completely at rest with respect to the source. And so, so what they did, they basically plotted as a function of, this is time running vertically, and horizontally is the period that they measure minus some reference number. And you can see that the period, which are the dots, changes like the black one, the filled one, or the measured values. and the open ones are, I forgot what they are. Sorry, I forgot exactly. But they kind of like show this like pattern where the period like changes as a function of time. But the solid line that you can see is basically the prediction to the correction you would expect to the period. That's just due to the, you know, the barycentering of the period. So you can see that it just follows really, like the data points follow the lines very well. So this means that, you know, we know the position in the sky, and then it's just the transformation of the topocentric periods, like the ones that are in the frame of reference of the observatory, to the one that's like in an initial frame compared to the pulsar. The thing though is that these corrections, right, they depend on the position in the sky that the source is located, especially like the position compared to the ecliptic. And so they could use, you know, they could essentially try to fit the correction to apply, you know, find the best fit. And this basically gives you a value for the position in the sky of the pulsar. So the right ascension is quite easy to measure because that corresponds to the transit of the object, but the elevation is much more poor, you know, with their telescope, because the localization was not very good. So they could try and localize by observing a different declination, but ultimately it's the timing, what we call the timing position. So basically getting the conversion of topocentric to barycentric coordinate system right, which basically enable the measurement. In the paper, they also speculated that if that source was in a binary system, one could potentially measure the Doppler shift, you know, of that source. So it would not be constant, but also would show a Doppler shift as the source orbit around, you know, another star or something like that. So this was quite insightful because, you know, it's something that's obviously these days we're doing on the daily basis. They saw the source varying. So these are observations at different times, and you can see the source varying widely. Sometimes it's not even detected, and sometimes, you know, it varies by a factor of like, you know, an order of magnitude. And even within an observation, which is the top panel, you can see the source varying a lot. And they speculated that scintillation, a bit like the same type of scintillation that caused their quasars to, you know, for the primary purpose of their instrument, could be the cause to, you know, things like the day-to-day scintillation. But for essentially the pulse-to-pulse or the short time scale scintillation, this was basically too fast to be explained with the, you know, what they understood of the scintillation, you know, interplanetary, or even nowadays the interstellar scintillation. So actually, a lot of what they saw during an observation in terms of variability is the pulsar intrinsically varying. Then they could also try and measure parallax for the source, you know, because they have an array of detectors, so they can phase it up. And if the source was, say, in orbit around the Earth, they would have measured. And essentially, they could put a lower limit of 1,000 astronomical unit to the source. So it had to be further. The other thing is that they observe at different radio frequencies. They only had like a really small bandwidth of about 1 megahertz, but they could observe at different frequencies. And they did so also simultaneously at some point. And they realized that the pulsations were out of phase at different frequencies. So there was a sweep basically of the signal at different radio frequencies. And they correctly ascribed it to what we call the dispersion delay. And I'll get back to that in more details, but they could use that and assuming essentially a density of electrons in the interstellar medium to infer distance to the source of something like 65 parsec. Now with more up-to-date, you know, measurements these days, we know that the distance is about 300 parsecs. And that's because we have a better model for essentially the distribution of the electrons. But still, this was remarkable that immediately, you know, at the first pulsar, they were able to measure that and also figure that we could use that dispersion to infer distances. The other thing is that the pulses are very short in duration. And that is really crucial, you know, in physics, because the source is very bright, and they basically already knew that, you know, the amount of radio flux we were getting, given the distance of the source, likely implied that the source is a current emission process. And therefore, if you have current emission, you know, it means that there needs to be a causal link between all areas of the emitting region, because otherwise, you know, you could not synchronize the wavefront. So if you have a point on a star and a point on a different point on the same object, right, that emits light that is coherent, they need to be linked so that at the speed of light, right, they can essentially exchange information within the time scale of the variability, basically. So this means that like C times delta T needs to be, you know, giving an upper bound to the size of the object, which was basically about 5,000 kilometers. So already they knew that it was likely coming from a compact object. And in the paper, they speculated that, you know, it could be radial pulsations from compact objects, either white dwarfs or neutron stars. And I've scratched it off because obviously these days we know it's not the real explanation, but there had been work on equation of states, and people had figured that compact objects, they could vibrate, you know, they could experience radial modes. And these modes, like for the typical white dwarf density, would be at about 8 seconds at the shortest. So they would only see harmonics, right? Given the signal was 1.3 second, they would only see harmonics, but they didn't see the fundamental. So they were a bit dubious it would be a white dwarf. But then they thought maybe a neutron star could fit the bill, because the higher density means the frequency is higher and can be anywhere from like the sort of millisecond to the second time scale. But then later on, like, you know, this didn't hold, and we'll see what, you know, what the real underlying reason was. Okay, so that's the sort of basic, you know, discovery material. Then I'll go through some basic pulsar and neutron star science. And actually, I'll follow some of the early papers, which, you know, I've made like some of the key contributions to the field, and also I'll balance it with some of the more recent work. So immediately, like a couple of weeks after the first pulsar was announced by Uish, Bell et al., people at Jodrell Bank, you know, also observed that CP1919 source. In fact, it was Lovell and Smith, Graham Smith as well, Sir Graham Smith, who actually were in touch with Uish, because, you know, they had just built like the big, you know, Lovell telescope, well, the one we know these days as the Lovell, and they basically knew that they had found that pulsating source, and so they already started the observations before the publication was made, thanks to Uish tipping them. So in that paper, they measured very accurately essentially the time delay as a function of frequency that was observed for the pulsation. And this is basically what we call the dispersion delay. Also they saw these strong fluctuations in the pulsar, and they also measured the spectrum for the pulsar. And what they found, slightly astonishingly, I would say, is that the pulsar was brighter at lower frequencies. So the spectrum followed a power law, and it was brighter at lower frequencies. But usually typical like synchrotron mechanism, like, you know, or other radio emission, like the free emission, tend to have a rather flat spectral index, and galaxies as well, they tend to be either flat or sometimes even a bit positive. So to observe quite a negative spectral index was actually in a way a bit different from what they had seen in other stars. So now let me cover a bit the concept of dispersion measure. It's the fact that, you know, the group velocity of light is frequency dependent when if light travels in a dielectric medium. And, you know, space, you know, even between stars, contains particles, you know, like electrons, right? It's a plasma, very low density plasma, I'll grant you that, but there are particles. And so this means that, you know, basically the speed of light is different from being exactly, you know, c, or 300,000 kilometers per second. So it's slightly different. And you can actually, you know, derive what the dispersion relationship should be, and then infer what the time delay for light that's emitted from a source at the same time, but would be observed by an observer somewhere else as light propagates through that medium between frequency nu1 and nu2. And basically the frequency delay varies as the inverse of the square of the frequency and is proportional to two constants. The first one is basically, just physical constants. But then the second part is basically the integral over the propagation path of light of the electron density. Okay, so basically the amount of delay is proportional to the column density of electrons along the line of sight. Okay, and so this means that if you have a real signal that you observe here, it's one that is in the sort of what we call the L band, around like the very famous 21 centimeter wavelength, where neutral hydrogen emits around 1400 megahertz. You can see the signal is basically coming later at lower frequencies. Okay, and the thing is, if you don't correct for that sweep in the signal and you just combine the information at all frequencies, so that you have a time series where you see the pulsations, but with all frequencies combined, so that you can build up the signal over all frequencies to have a brighter pulse, then it will be smeared because of that sweep. So in a typical pulsar observation, what you need to do is to shift the various frequency channels according to this slope, in order to line them up before you can combine the signal and then get a very nice and clear pulse. Okay, and like I said before, the delay is basically inversely proportional to the frequencies. So depending on the instrument you observe with, then you have different amount of delay. But when you observe with an instrument like LOFAR, for instance, which observes in the sort of like range of about 100 megahertz, you can have a delay that is of order of something like a second per unit of dm. Okay, and typical pulsars, like the nearest pulsar, has a dispersion measure of about a dm of a few, but we observe pulsars closer to the galactic center, which have dispersion measures of something like the thousands. Okay, so that means literally the signal at a very low frequency from the galactic center compared to one at the gigahertz frequency range could come basically half an hour later. Okay, so this is a very, very significant thing. If your bandwidth is very narrow, obviously the sweep across the band is not too important. So that's why Bell, for instance, when she first observed the pulsations from CP 1919, because the bandwidth was only 1 megahertz, it didn't smear the signal too much. And then then when they observed with various frequencies, then they could see the sweep. But these days we have there are instruments with the GBT or parts and such, which have fractional bandwidth that are almost like 100%. So that means if you observe at 800 megahertz, the actual band can go from 400 to 1200, and in which case the sweep across the frequency range can be massive. Okay, so this is really something important, but also so it's a bit of a hindrance, right? Because when you deal with the data, you need to correct for it, but also if you search for new pulsars, you don't know what the value is a priori, right? So you need to guess what the value will be. And it means that when you search for pulsars, you basically need to do a brute force dispersion of the data. You need to take the data, disperse it at all kinds of values in order to correct for the potential delay. And then you search for pulsations, using, Fourier analysis and such. So so searching for pulsars is extremely CPU intensive, from the fact that you have to correct for a delay that you don't know a priori. But once you know the pulsar, then it becomes a really good ally, because the dispersion can be used as a distance proxy. So if obviously what you measure is only the integrated column density. But, here's a projection, so that's from a recent paper from Yao et al., which is the modern version of what used to be called the NE 2001 model. So their model basically for the electron distribution in our galaxy. So you have the center of the galaxy here at 0, 0. The Earth is at 0 and about like 8 kiloparsec up on the y-axis. And then you have the location of a bunch of pulsars, basically, that have been measured independently from the dispersion measures. So they're typically measured using a parallax that's measured, with radio interferometry. And so if you know the exact distance of all these sources, then this means that, for any of them, the total integrated electron density along that line of sight. So if you have enough of them, then you can start building a 3D map of the electron distribution in our galaxy. And people started doing that in the 80s even, and there's been various iterations of models, but the two kind of most used and most famous ones are the NE 2001 from Cordes and Lacio, and the Yao, Manchester, and Wang from just a few years ago. And this is the latest one. So basically, they usually use a bit of a description for a galaxy that is semi-empirical using, we know there's probably a ring of ionized medium that's like kind of at mid-distance to the galactic center. And then there's an overdensity, obviously, of the electrons at the galactic center. And then there are spiral arms. And also in our no-cold neighborhood, we know there's a bubble of ionized medium as well. The solar system stays in a sort of local bubble. So they use various like components, and then they use the actual data to adjust. But this means that we can measure an approximate distance to any new pulsar using the dispersion measure that we obtain. So that's really interesting. Then, back in 69 or 68 rather, there was another paper by Andrew Line and Barney Rickett, where they looked at the first 4 pulsars that had been detected with the now Lovell telescope. So back in the days, it was called the 250 feet telescope. And they measured a spectrum for them. And as you can see, most of them have essentially, are brighter at low frequencies. So they have, like essentially, negative spectral index. And they also concluded, because of the sort of approximate distance they could get, that the emission, the brightness temperature, so the amount of light produced, by the objects, given their presumed size, was too large to be incoherent, like black body emission, for instance. So it had to be something like synchrotron emission or a process like this producing the light. And they also looked at the variability of these sources. So now, in modern days, we have like a good understanding of what the pulsar spectrum looks like, for instance, in the radio. And there was a recent study in 2017, basically looking at the spectrum of a large number of pulsars. I think they had like something like something like 1,000 of them or something. And that's a typical pulsar spectrum. You can see various measurements from like a given instrument that's got large bandwidth, but then also other instruments. And so pulsars typically follow a power law spectrum, where the alpha index on average is something like minus 1.6. But there is quite a spread. So you'll find some with nearly completely flat spectra, and some that are even very, much steeper, around like -3. There's also other pulsars where the power law doesn't fit very well, and you'll see a break in the power law. So sometimes you might have like a composite of like 2 power law, or some even have like spectra that like is basically all bent around. And, to be honest, like this is mostly like empirical measurements, because the actual full physics that explains the perfect shape of them, is still a very active area of research. Getting back to the early days, there was also the discovery of magnetic fields from the interstellar medium by Graham Smith. So basically, observations that were done at different frequencies, but with polarization, revealed that the pulsars, the pulsar signal was highly polarized, especially linear polarization. But the other thing is that the linear polarization was shifted at different frequency. Okay, so if you measure the polarization angle, basically, you would find that the angle would shift at different frequency. And this is what we call the Faraday rotation. The modern view is basically there. That's pretty much the state of the art. So if you have light propagating through a magnetized plasma, the right-handed and the left-handed circular polarizations will travel at different speed in the plasma. Okay, so that's like sort of basic electrodynamics. So if you have like a wave that is linearly polarized, right, completely linearly polarized, you would have a mixture of left-handed and right-handed polarization, right? The two sort of orthogonal polarizations that you can mix together to make a wave that is linearly polarized. And the polarization angle is just basically the phase shift between the left-handed and the right-handed polarization. Now, if your speed is different for the two polarization, this means that as the light propagates, then the delay would essentially, accumulate for one handiness to the other. And therefore, the plane of polarization will therefore rotate as a function of position in your magnetized medium. But also, the amount of rotation will be different at different frequencies. And so it basically varies. So the actual rotation of the linear polarization depends on the square of the wavelength. Okay, and it's proportional to something that we call the RM, which is the rotation measure. And so the rotation measure is a bunch of constant times the integral of the electron density times the magnetic field in the direction that's parallel to your line of sight. Okay, so by measuring at different frequencies, the amount of rotation of your swing of your polarization angle, you can basically infer this RM value. And then if you recall from a few slides ago, the dm was the integral of any dl. So this means that if you take the RM and you divide by the dm, you effectively get a measure of the average magnetic field. And so this is really handy because now not only can you probe the overall average density of electrons in the interstellar medium, but also you can probe the average magnetic field. So there was a recent paper by Sobe et al. Where they did that sort of measurements using a large number of pulsars. So they used values from the sort of existing literature for 1,100 or so pulsars, but also with the LOFAR telescope, they had like very accurate measurements, like better than before, because the LOFAR operates at low frequency where the swing is more important, basically. So that for 137 pulsars. And these are like the squares and the circles that you can see. And the color map is the value that you measure for the rotation measure, but using galaxies. So you can also use, for instance, the light from some radio galaxies, which is partly polarized, to also measure like that magnetic field. But the problem is that given the galaxies are very far, you cannot probe the 3D structure of the magnetic field of our galaxy. You just have like the total integrated component. So, so having measurements from pulsars is also quite useful. Okay, so now I'm going to shift a little bit away from the sort of the physics of like interstellar medium and such, and move to the physics of like the neutron stars themselves. So the sort of modern view of pulsars is that they are basically lighthouse, rotating light, cosmic lighthouses. So you have the small object, something like 10, 15 kilometers in radius and masses of, more than a solar mass with huge magnetic fields, and they spin quickly. And unlike the original idea from Hewish et al. That said it was pulsations from a compact object, it didn't take long to realize that it was actually beamed radiation from the object that spins. And so as a result, the beam sweeps across your line of sight, and then you see a flash of light. The idea of that rotating lighthouse was by Pacini and Gould, who both independently came up with the idea in '68. And actually, Pacini had basically formalized, the idea of the neutron star that could emit beam radiation even before the first pulsar was basically discovered. So it was really insightful. And I think we should probably look to take a break in a few minutes. I might just show you just this one slide, and then we can take a break. So just so I can finish this this topic. So if you have a rotating, essentially a pulsar is a dipole, according to Pacini and Gould, and then the modern view, it's basically a magnetized dipole that spins in vacuum. And if you have, if you look at simple electrodynamics, a spinning dipole basically produces electromagnetic waves, because it's a time-varying magnetic field. And so the induced Poynting flux basically carries energy away, and that energy is taken from the rotation of the object. So you expect the pulsar to naturally slow down over time, just because it's producing electromagnetic radiation. And so this was observed, and it didn't take long. Within a year or so of finding the first pulsar, people had already had like a good dozen or so pulsars, and they had measured not only the spin period but also a linear change in the rotation of the object. So P, and what we call these days P dot, so the time derivative of the period. And so this leads to what we now call the very famous PP dot diagram. So you probably will see like this plot at every pulsar or neutron star talk that you're ever going to go to. So you can basically display the period derivative as a function of the period for all of these objects. And to first order, most pulsars, they basically are well described by just these two parameters. Young pulsars, they spin down quite fast, and then you can measure a second derivative to the period. But most pulsars, you don't even measure a second derivative. So just the period and the period derivative are sufficient. Now, if you do simple kind of like electrodynamics, you can actually infer the dipole magnetic field from these two quantities because of the fact that the slowdown rate is proportional basically to the magnetic field. So you can basically turn things around and infer, how strong is that bar magnet, that is spinning. And it basically depends on the root of the period times the period derivative. So on this plot, right, you can see lines of constant magnetic fields for, the pulsar population. And so the magnetars at the top, I think you'll have Diego will give a talk which will go over like the various kinds of neutron stars. But the magnetized ones, magnetars, they have like 10 to the 14 Gauss magnetic field or more. The average population is around 10 to the 12 Gauss. And then the lowest magnetic fields that we see in some pulsars, the binary ones actually, are of order of 10 to the 8 Gauss. So it's a huge dynamic range of magnetic fields. The other thing is that you can infer from the slowdown how much energy is radiated in that sort of Poynting flux. And it's basically proportional to the spin down and inversely proportional to the cube of the period. And these describe lines that are like in that way. So basically the energetic pulsars are like, the ones in that sort of like wedge. So the crab pulsar is basically one of these two there, I think this one. And so you can see like, these pulsars are very energetic. And when you go to the bottom there, like towards this line, then they're very low energy pulsar. And the last thing is you can infer a time scale for the pulsar, which is basically, the period divided by the period derivative. And that gives you an idea of like how old the pulsar is. And these are basically the lines that you have here. So the young pulsars are towards the top and the old ones are towards the bottom. And to first order, it sort of works for the young pulsar, like the crab pulsar, for instance, has an age of about 1,000 years. And the spin down age that you get if you derive, take this formula is something of the order of 1,000 years. But yeah, so that gives you an idea of like the age of pulsars, which is quite handy. Okay, so I think we can take a break now, perhaps. I don't know if we want to do some questions first or take a break or other way around.
Okay, Rene. So, well, I have maybe one or two questions, but if people want to ask questions online for any of the lecture up to now, please feel free to put your hand up. There is this like hand up tool that you have in Zoom, or if anyone here. I don't see anyone at the moment.
Yep.
Maybe I'll ask one or two things. So to go back to this model of the galaxy of the dispersion measure, well, okay, the electron density, what you showed was in 2 dimensions, but obviously galaxy is not completely flat. So is it necessary to have like a 3rd dimension model?
Yeah, very much so. So there's a bit like the sort of when people model the stellar density, right? They have like a thick disk and a thin disk, and there's a scale height. So the model for like the spiral arms and the sort of ring, they also have like a Z component, a vertical component. And yeah, and that part is actually a bit more difficult to get because, a lot of the pulsars you find along the plane because, that's where the massive stars are. And only the older pulsar have had time to move away from the galactic plane and form like a more like sort of a slightly more isotropic, distribution. So the uncertainties on the model tend to be higher when you look at higher galactic latitude, in fact.
Right. So when you talk about the old pulsars moving away, I mean, maybe this is jumping ahead a lot in terms of the subject matter, but does this tell us something about the pulsars were given some kick, some linear momentum when they were formed, and then you could possibly deduce what sort of order of magnitude that was?
Yeah, that's right. So yeah, it's not a topic that I will actually cover today, the pulsar kicks, but I think one of the best papers is Torres et al. I think 2017, which I'm co-author on, and basically that paper is about double neutron star systems that contain a pulsar, and for which we can measure the eccentricity of the orbit very well, and in the paper, basically, there's been modeling of the kick of the supernova because you have 2 neutron stars. That essentially it's the second neutron star that caused most of the eccentricity because the orbit was probably quite circular just before. And so by looking at how eccentric the orbit is, you can basically have an idea of how much mass has been lost in the system and also like what direction the kick was. So obviously it's all probabilistic, but when you have enough of these, then you can actually study, essentially you can have if you have a big kick that is in the direction of the orbital motion, you're more likely to, cause a large eccentricity than, if you have a kick that's opposite, for instance. So, so it turns out that, yeah, like there's quite a range of kicks, but, they tend to be in the sort of order of 100 kind of kilometers a second or so. And then when that kick takes place, right, it also gives an impulse to the pulsar. So if the pulsar is isolated, for instance, it can like start flying off, in the galaxy, in a different direction from the original bulk motion of the star in the galaxy. And that's why like old pulsars you can find at like, high galactic latitude because they tend to eventually diffuse out and from the kick that they've had. Yeah.
Great. Yeah. So maybe I'll ask something about the PP diagram, PP dot diagram.
Yeah.
There seems to be kind of a limit on the top edge. Well, there's no pulsars that estimated to have to be younger than 1,000 years old. Now, in principle, there's maybe, well, order 1 galactic supernova per 100 years-ish.
Yeah.
So this is within an order of magnitude. So is that some sort of relation you can make? Like, what do you expect the youngest pulsar to be based on the rate of supernova?
Yeah. So there's been so for instance, there was a paper by Fauché, Giguère, and Caspi, like around maybe 2006 or so, and other people also have tried to simulate the PP dot diagram, right? They create like essentially neutron stars, a pulsar, they give it an initial period, and then they make it evolve in that diagram, and then one of the ingredients is the supernova formation rate. But the thing that and usually, I mean, most simulations are consistent, with what you said, like a rate of a couple of like supernova per century in the Milky Way of order 1 to 3 or something like that. The reason why there's none, kind of like much younger is basically because most of them, they will tend to explode, but on, not necessarily near us, right? So if you look at this picture of the galaxy, right? This one is biased because that's like the position of pulsars with measured distances. But the actual, if you were to put every known pulsar, on this diagram, you see that most of them are basically in a wedge that's like that, basically compared to like the center of the galaxy. And that's just because, the further you look for them, okay, they're fainter, but the main enemy really is the amount of dispersion and material also that's, in the way. So at the moment, we've kind of explored like more or less like mostly one quadrant of our galaxy, and the rest is kind of a bit less explored. And so, just like the fact that, naked eye supernovae from our galaxy have been very rare in the recent history, right? I mean, there's Tycho Brahe's supernova, which I think was probably one of the last ones. I forgot if there was maybe another one after, but yeah, in the last sort of like 400 years or so, 400 or 500 years, there's been very few, even though they should have happened. So it's probably that the ones that have happened were far from us. And so likewise, the pulsar that's connected would probably not be visible. But also in the second hour, I'll talk about, some younger, we know of some younger supernova, some younger neutron stars. For instance, there's one in Cassiopeia A, in Cas A, supernova remnant, but that one does not produce pulsations. So it's a radio quiet neutron star.
Okay, Ricardo, if you move Rene's little window, well, we can see that there's a pulsar in the top right of the plot, which is, at the moment is underneath the window. Yeah, exactly. So the one with the highest period derivative of all, is this special in some way? Or, well, I guess it's not really outside the distribution. It just happens to be.
You mean like this one?
Yes, I mean, oh, okay. It has the highest p dot, but otherwise,
yeah,
regular one.
Yeah, so yeah, the ones here with the blue triangle, they're the ones we call magnetars. So the magnetars are like extremely magnetized, as the name sort of alludes to, and it's believed that most magnetars we can probably see only for maybe like 10,000 years or so, and there might be also like slightly strange physics going on in the sense that the magnetic field might change over time, in these objects. It's not quite clear already, but some people speculate that the magnetic field in magnetars might decrease over time, for instance. So and they spin down very quickly. So there could be young magnetars that would be somewhere there, but we haven't detected yet. And then because we typically find them from their outbursts. So they could be spinning down real quick, and before you can see them, they might be gone, down there.
Okay.
Yeah.
Let's see. Well, I don't have any questions. more at this point, but if people want to put their hands up or say anything. Okay, well, maybe we take just 2 minutes. If you want to have a drink of some sort, and then we'll come back in 2 or 3 minutes.
Yeah, I mean, whenever you want. I mean, I know you probably don't want to all sit, forever. So maybe if everyone just wants to get up or walk around the room for a turn or something, I'm happy with this.
But yeah, just a couple of minutes, and then we'll start again.
Yeah, just stretch for 2 minutes and yeah.
Okay, thanks. Yeah.
Cool. Okay, so now, yeah, we're starting to move more and more away from like the kind of like early papers and look into the more modern science. But it started really with the work of so we just finished with the dipole model of pulsars and this sort of lighthouse idea, and within a year basically of the first pulsar being discovered, Goldreich and Julian had like a very sophisticated model about the pulsar electrodynamics. It's like a sort of like 15-page paper or so. It's a really good read, but also a tough read, at least for me, who's not like, not so good with electrodynamics. But basically, the idea, like I said earlier, is that you have like a dipole, right, that spins, and therefore you have a time variable magnetic field. And so if you have a time varying magnetic field, then this means that you will induce an electric field. And so in the simplest picture, where the magnetic field is aligned with the spin axis, you can sort of see how the electric field would be essentially parallel to the surface. And then if you do the calculation, you find actually that the electric field is way larger than the gravitational field near the surface, which seems almost like surprising given how compact and dense the neutron stars are. So you have particles pulled off the surface of neutron stars. So that's something that like takes place normally, and therefore the neutron star surrounding is expected basically to fill with a plasma that's partly sourced from the particles at the surface. This plasma and the overall magnetic field will therefore produce a charged relativistic wind. And from like the simple idea of the vacuum dipole, Goldreich and Julian inferred that there has to have a charge density of particles in so this is the picture of like the neutron star. So you have the spin axis, and then you have, in this case, they made it like an arbitrary inclination angle for the dipole, the magnetic dipole of like theta naught. And therefore you have like field lines that wrap around like this and will reconnect to the other pole. But then at a certain distance, which we call the light cylinder, a field line that was trying to co-rotate with the surface would have to go faster than the speed of light. And therefore, that field line cannot be co-rotating with the star. And so the field line would be left open, basically. And so there is a region around the pole that we call the polar cap, where a field line would never reconnect because it has to co-rotate faster than the speed of light. And so the region of the magnetic field that is closed is what we call the pulsar or the neutron star magnetosphere. And it's believed to be filled with plasma. The other thing is that when you look at the electric current that's generated, there's basically a line essentially breaking the region where you should have a current with positive charges flowing outward and negative charges flowing inward. Flowing outward rather. So you have like this magnetic sheet basically of current. And this region is quite important actually for the emission process of pulsars. And I'll get back to that. But you can imagine that there's then this wind that's been produced. And I've got like two neat videos to show you. So they're by Anatoly Spitkovsky, who's one of the experts in modern pulsar electrodynamics. So this one is basically the structure of the last open field lines, you know, the one that extend to the light cylinder for a dipole that's spinning with like the plasma that's expected to fill the you know, naturally. And we call it the Goldreich-Julian density. And it's basically the product of the rotation by the magnetic field, basically, in the direction parallel to the magnetic field. And so a typical density would be something like, you know, 10 to the minus 3 times the magnetic field in Gauss divided by the period in seconds, particles per cubic centimeter. So people, like, already in the 70s, they were trying to solve, you know, the problem of a rotating dipole, and in what, you know, it's called the force-free problem, where, you know, basically it's in the static case, where you have like a equilibrium reach, and you don't have like extra plasma coming into play. But people have managed to solve, you know, the aligned dipole and also a perpendicular dipole at some point. But when you include the effect of plasma and dissipation, then this is hugely complex problem. And so it's only like essentially in the last decade or so that people have been able to do simulations that we believe are realistic to really produce an inclined rotating dipole where you take into account, you know, the full plasma also that's in the magnetosphere. And so that's work that, like, you know, the likes of Spitkovsky, Belodoborov, and others have done. And this, you know, in this one, you can see, for instance, like the neutron star, and you can see the magnetic field lines as the pulsar or the neutron star rotates. And you can see essentially that's the color scheme is indicative of the plasma density, but also the color shows you the charges, like between the blue and the brown, so it's different charges, and you can see essentially this sort of like spiraling pattern of alternating charge, you know, positive and negative, that dissipates around the neutron star. The electrodynamics is also you know, tightly connected to the pulsar emission mechanism. There are basically 3 primary regions where we believe that the pulsed emission from neutron stars, you know, at any energy can come from. The first is what we call the polar cap. And the polar cap is basically the region around the star where the field lines coming out of the neutron star will not close within the light cylinder. So it forms basically a sort of like a wedge, if you want, a 3D wedge that, you know, goes with some opening. And so that's the first region. Then there's another region that's called the outer gap. And the outer gap is basically the region that's just basically outside, you know, on the last sort of closed field lines in between the light cylinder, where the light cylinder is located, and that line, you know, that line that differentiates the region where you have a return current of positive charges or negative charges. And then finally, there's what's called the slot gap, which is basically like the tangential region following the last closed field lines. And people have, like, there's a large number of models, like, to explain like how, you know, the pulsed emission might be produced from, you know, one or many of these regions. And I in this talk, you know, I'm not going to go through like all of them, but basically the general idea is that you have plasma, right? And then if you have an electron, for instance, it will follow the field lines. And so it will basically, you know, if an electron has a, you know, a proper velocity, it will move in a direction, but then it would start to gyrate along the field lines from the Lorentz force. And therefore it will gyrate, so it will propagate through, like, you know, this sort of like helicoidal pattern along the field lines. And so if you have charged particles that propagate along the lines which are open, they will basically be, escaping through like the pulsar wind. But also as they gyrate, the charged particles will produce, well, cyclotron radiation, but also because they're moving at relativistic, velocities, that will produce synchrotron radiation. So you can imagine charged particles producing synchrotron radiation. Also, the ones that propagate along the curved field lines like this, they also not only produce synchrotron because of the gyration motion, but also they will produce synchrotron from what we call curvature radiation. The fact that the overall motion of the particle is also going in a curve, and therefore this produces synchrotron. And then these high energy particles, they can Compton inverse scatter with, other particles, electrons in the magnetosphere, and then kick them. And then these particles can be accelerated to high energy. And then these particles can then pair produce. And then essentially there's usually a cascade of particles that are pair produced. And these particles will end up, producing, various kinds of non-thermal emission, synchrotron or inverse Compton for the most part. So this can produce high energy radiation, in the gamma rays and X-rays. But also you can imagine that essentially the counterpart of this very high energy emission would also produce radio emission, from the milder relativistic electrons, for instance, that just produce, synchrotron, in the magnetic field. That will produce emission in the radio regime. So for this reason, pulsars or neutron stars tend to be visible from their pulsed emission across like the entire, electromagnetic domain. So this is represented, in this sort of wide spectral energy distribution here. So in blue, so this is the Crab pulsar. In blue, this is the nebula, like this. This is the spectral energy distribution for the nebula that surrounds the Crab pulsar, and the black points are the pulsed emission, so the pulsar itself. And so they emit, up to like TeVs, for the Crab. And then you go like in the regime where you have the X-rays, and then you have also optical emission. And then there's a bit of a gap. So the Crab pulsar is not really seen pulsating, in the sort of microwave regime, but then it picks up in the radio regime. And then in the radio regime, most of the Crab pulsar, like I said, has this, or like other pulsars, this like a negative power loss. So it basically gets brighter at low energies. And then eventually, like any process, it should turn over somewhere, otherwise the amount of energy would be infinite. So at the lower radio frequencies, then it turns over. And so a bunch of pulsars have been seen across the electromagnetic spectrum, in the radio, but also even in the optical. So there's a handful of pulsars that are seen to pulsate in the optical. They're quite challenging measurements to make because the luminosities in the radio in the optical are very small, and you need very fast cameras. But like the Crab pulsars, like in Vela, or notorious examples of pulsars that actually pulsate in the optical. And then the gamma ray and the X-rays are another domain where you see it very prominently. Okay, so that's all I'm going to say for pulsar emission. You can ask questions, if you have more later. But now I want to talk a bit about various uses that we have for neutron stars, to study fundamental physics. So the first and most obvious one, perhaps, is testing gravity. Because they're such compact objects, we can imagine that effects of general relativity are extreme. And a lot of that work started with the discovery of the very first pulsar in a binary system, which was found in 1974 by
Rene.
Yeah.
Sorry, because you said that we can ask questions concerning the pulsar radiation.
Yeah.
So what are the properties of the neutron star that enter this calculation? I mean, I know it's a model, but so it's, for example, the radius and the spin rotation, or the angle. What are the properties or the parameters that will make the spectrum to be in one way and not the other?
Yeah. So, by the way, it's not like my area of expertise, but from what I know, so the internal properties of the neutron star are more or less irrelevant for the pulsed emission that we observe. So usually, like the radius and the mass are not really inputs for these models. Maybe for some of the more like advanced, like, high energy models, but usually they're really all about like what's outside of the neutron star. So typically the magnetic field is, a very important parameter, right? Because the most important one, arguably, because it's really the magnetic field that drives, the charged particles that then, pair produce and such and emit the non-thermal radiation. So magnetic field, rotational speed of the star as well, because also this determines, like, for instance, the faster the star spins for a given magnetic field, then the smaller would that light cylinder be, right? Because you cannot go too far from the surface to get the point where you would have to travel at the speed of light. So rotation period is one other. Then there's the plasma density in the magnetosphere, and that is one of the big I think one of the main challenges in the modern pulsar emission models is basically understanding how the interaction of the plasma with the magnetic field, and also how that plasma will dissipate, because if the plasma remains highly magnetized at large distances, then this means that you will be able to produce synchrotron radiation very far off, whereas if the magnetization falls very quickly, then you won't be able to produce it at a large distance, for instance. So for all of the structure of these gaps or the polar cap, the details of the electrodynamics is really important. But all of it is basically outside of the neutron star.
Yes, I understand. But so the composition and the properties of the plasma are related with what?
Well, to first order, I mean, it's basically electrons, and then basically, hadrons, but typically you can just imagine that there would be just protons, basically. So I'm not sure that the plasma is very complex usually when they're modeled in terms of atomic, mixture.
The density, for example, is just fixed by the magnetic field again, or is there anything else?
Well, so yeah, okay. So in the simplest model, right, you would predict that the density, in the closed magnetosphere, should be the Goldreich Julian density, and that's just depending on the magnetic field and the rotation, like I said. However, when people model the emission, there's essentially a multiplicity factor, that is a model-dependent quantity that is introduced, and then people tend to find that the density has to be larger than the Goldreich Julian density, for instance.
Because you need more radiation.
Yes. So basically, essentially to reproduce the flux, but also you need a certain number of collisions and such, for instance, to have the right amount of pair production, and then get the right amount of radiation. So then you need to tweak, things like the plasma density. Yeah.
Okay. Thank you. Thanks a lot.
I have a related question, Rene. Maybe you didn't have time, but probably, I mean, glitches in the rotation frequency, they could provide some information on the internal structure of the star.
Yeah, that's right. If you allow me, I'll just carry on a bit. I'll get to the interior of the star in a couple of slides, and maybe I'll kind of address some of that, actually, if that's okay.
Perfect. Yeah, sure.
Yeah. But yeah, but the modern models, so I can give references, in the slides, when I share them afterwards. There's been a lot of work. For instance, Alice Harding, is one of the leading experts in the high energy emission, and then they're really at the stage where they're able to like model the magnetosphere and the plasma distribution, and then they essentially follow all the pair cascades, and then the synchrotron takes place, and they can actually produce essentially a map of where the high energy emission should be as a function of like essentially rotation phase of the star and the magnetosphere. And then when they observe like gamma ray pulse profiles, they're basically able to infer the geometry of the neutron star. So basically, if you change the magnetic inclination, right, of the magnetic field compared to the spin axis, you'll get also a different geometry where the emission takes place. And so they're able to like essentially fit for the geometry of the magnetic field compared to the rotation of the star. And then by tweaking things like the density and such, then they can vary like the sort of like luminosity and such. So it's getting pretty good thanks to the the high energy missions like Fermi, which are producing really high quality data that can be modeled. Yeah. So okay, so I'll now switch to gravity, and then you'll see I'll get more and more towards like talking about the actual neutron star itself. Yeah. So the first binary pulsar was found in 74 by Hulse and Taylor at Arecibo. They found basically that the pulsar had like this Doppler shift that indicated that even when corrected for the barycenter of the solar system, there was still a Doppler shift that repeated every 7.75 hours. So that was the first binary pulsar. And what's really interesting is that the orbit is very eccentric. So when you look at the radial velocity as a function of orbital phase, you can see that the velocity describes a pattern that's very skewed, like it's got like this very kinky thing. So if the orbit was circular, you would expect a sinusoidal variability in the orbital velocity. But the fact that the orbit goes from like a low velocity and then increases very quickly to high velocity means that the orbit has to be eccentric. And then they inferred the mass for the companion and deduced that the companion has to be a neutron star. So this was the first pulsar neutron star system that was found. And it turns out that these neutron stars are actually very rare. There's only about like, just over a dozen of pulsar neutron star systems that have been discovered so far. The vast majority of pulsars in binary system have a white dwarf as a companion, and they're quite circular orbits. So that's out of the sort of like 300 or so pulsar in binary systems. So now I want to talk a bit about how we test gravity with neutron stars, with pulsars. So the timing of the Doppler shift can enable you to measure Keplerian parameters. So you can measure the orbital period, the orientation of the orbit, that's what we call the ascending node. Then you can measure, a reference epoch for where the orbit, where the pulsar is in its orbit. You measure the eccentricity. So there are 5, or Keplerian parameters as we call, but what we measure, right, is the radial velocity basically of the star. You don't know anything about the component that's perpendicular to our line of sight, in the plane of the sky. So as a result, you don't have enough information to solve for, the masses in the system and know the orbital inclination. So if you were to know 2 more pieces of information, then you could characterize the system entirely. So from the simple Keplerian parameters that you measure from just timing the pulsar, period across the orbit, you don't know what the 2 masses in the system are. So often we display, the constraint for gravity on what we call mass diagram, where we plot the mass of the companion as a function of the mass of the pulsar, that is observed. And basically, at large velocities, you expect the orbit to start departing from a Newtonian orbit and become more and more relativistic. So it's quite complex, obviously, to solve for all the, the equation of GR for like the orbital motion. So usually what is done is that there is an expansion of the framework, the Newtonian framework, to include first order correction in velocity, basically. So you basically take the general relativistic metric, and then you take an expansion to first order in velocity, and this gives corrections to the Newtonian orbit, basically to first order in velocity. And these corrections, phenomenologically, they are essentially orbital perturbations in terms of time derivative of the Keplerian parameters. So you can think, for instance, of the eccentricity, right? Normally, a Newtonian orbit would have an eccentricity that would be fixed over time. If you neglect things like tides and non-purely dynamical effects from just the orbital motion of 2-point sources, like for 2-point sources, it should just be constant eccentricity. Then the orbital period should also be constant. Then the orientation of the orbit should also be constant. So general relativity basically will introduce departure of the constants of the Keplerian parameters. And so you can basically describe them with what we call post-Keplerian parameters, which are time derivative of the Keplerian parameters. And each Keplerian parameter is a function of each post-Keplerian parameter is basically a function of the other Keplerian parameters, but also of the masses in the system. So this means that if you measure a post-Keplerian parameter, so a departure from Newton's orbit, in the system, you essentially have one constraint in this mass-mass diagram. And then if you can measure a second post-Keplerian parameter, then this will describe a second line in this diagram. And then this means you can solve for the two masses in the system. Then if you can measure a third post-Keplerian parameter, well, you would hope, if your theory of gravity is correct, that it would intersect where the other two first intersected. And therefore, your theory is valid. But if you have another theory that doesn't work, then your post-Keplerian parameters would describe constraints in this mass-mass diagram where they might not intersect. And therefore, it shows that your theory is violating, the observations. Okay, so that's the basic principle for testing gravity. And now I'll just guide you through some of these parameters that can be measured. The first one is the periastron precession. And so this is the simple idea that the orbit, right, according to Newton, should be oriented in the same fashion if it's eccentric. But then, according to relativity, the orbit should actually precess over time. This was Einstein's big prediction, big explanation, in 1915, in his general relativity papers, in one of his 4 papers, to explain the precession of Mercury's orbit, which is seen to have this extra precession term of 43 arc seconds per century, right? So the orbit gradually drifts at a rate of 43 arc seconds every 100 years. And that part, no one could explain. There is a bigger precession part that is explained by the tidal effect of Jupiter and the other planets in the solar system. But basically, there was always this unaccounted for term that no one could explain until Einstein came up. And so the precession rate is basically, like I said before, it's like constants. It depends on the square of the orbital separation. Or the cube. I can't quite read very well, like on the original paper. It depends on the orbital period of the system and also on the eccentricity of the system. And so Einstein, given that we can measure Mercury's separation from the sun and its period and eccentricity very well, you can literally plug it in the equation, right, and get a prediction for what the advance of periastron, what the drift rate should be. And so Einstein in his original paper predicted that it should be 45 arc seconds plus or minus 5, given that these measured quantities are not perfectly measured. And yeah, the modern value basically, or is something like 42 point something. So yeah, but we can see it in binary pulsars. But because the orbits are quite tight and the masses are large, then this sort of drift is much more important. It can be several degrees per year, in binary pulsars. The other effect of relativity you can see is the gravitational redshift. You probably learn in a GR course that the larger the gravitational potential, the slower time would look from a distant observer, right? So that's essentially like gravitational redshift. And so in the orbit, right? So imagine that you have like an invisible object that orbits like this around the center of mass. And then the pulsar that you see orbits, on this line. Then at some point in the orbit, it will be closer to its companion than, half an orbit later when it's there and the companion is there. So because of the distance varying between the two objects, then the gravitational redshift will change because the effective gravitational potential that a photon has to climb to get out of the system will depend on the orbital phase. Okay, so you will see a delay, a time variable delay in the photon, like in the pulsations, basically, which is linked to the position in the orbit, okay, and the distance between the pulsars. So that's another type of effect. Then a third one is called the Shapiro delay, and that is due to the curvature of space-time. So you can imagine that, if you have light, photons traveling far from like a source of gravity, space-time is relatively flat, so they propagate just in a straight line. But then as you have photons that propagate, closer and closer to a center, source of gravity, then space-time becomes more and more curved. And so the photons basically have to go down, they follow geodesics. So they go in this curved space-time. So effectively, the photon is traveling a longer path when it travels in a more curved, space-time. And so this produces a delay. And that delay will be more important when the pulsar is located behind the companion star, right, that it orbits. So when it's located at the front, you're basically seeing the photons just traveling more or less in a straight line. But then when the photons, if you're observing from Earth here, when the star, the neutron star is behind its companion, then that's when, the gravitational curvature would be most important as it travels to us. So you'll have a larger delay when the two are most aligned. But also this obviously depends on the geometry, right? The more edge on the orbit is, the larger, the amount of curved space-time that the photons will travel compared to a system that is seen more face on, where, they travel basically perpendicular to that sort of like, curved space-time, they can escape more easily. So if you don't account, so this is basically like the residual, like essentially you try to demodulate, right, the orbital Doppler shift from pulsar as a function of orbital phase. And if you don't include a relativistic model, even when you account for like the drift in orbit and everything, you still have like this sort of little kink that appears in the data. And phase 0.25 is where basically the companion is most, is at what we call the inferior conjunction. So when the companion passes basically behind, in front of the pulsar. And so you see this little delay. Now, if you include what we call the Shapiro delay, right? You account for the curvature of space-time, then you can see like that you have like a much more well-behaved pattern. And then when you take it away, so this one is the residuals basically in the time of arrival by accounting for the Shapiro delay, but then kind of like putting it in the model, in the residuals, so we can see what it looks like, what this effect looks like. And at the top is an orbit that's been fully demodulated by accounting for the Shapiro delay. So these all give you constraints. So basically, the gamma here, so this is a mass diagram for the original binary system, pulsar binary system formed by Hulse and Taylor. So gamma is the gravitational redshift. Omega dot is the precession of the orbit. And then PB is the change in orbital period due to gravitational wave emission. And this one produces another curve. So this was a prediction from Einstein, right? That a body moving in space-time, accelerating in space-time, would produce gravitational waves. So if you have, for instance, a binary system, you have a motion of mass, and this should produce gravitational waves. And these gravitational waves would basically drain energy from the orbital angular momentum of the system. So as a result, over time, you expect the orbit to shrink due to gravitational wave emission. And this was observed about 5 or 6 years after the discovery of by Hulse and Taylor of the binary pulsar. Taylor and his then PhD student, Joel Weisberg, observed the decay of the orbit. So basically, they could just measure the orbit shrinking over time. And often we show it on a plot like this. So it's basically time. And this is the delay at which you see the pair, if you demodulate the orbit, then you would expect to be able to predict when the perastron will take place. And basically what they saw over time is that the perastron point was coming earlier every orbit, and this just accumulated over time. So this plot is from the original paper by Taylor and Weisberg in '79, and you can see that basically the orbit is becoming shorter, and after about like 5 years or so, the orbit was about 2 seconds shorter, okay, than you would predict. And then it just accumulates. And this is like from the sort of more modern version from 2005 by Weisberg and Taylor. So now the orbit is about, like the orbital period is about 45, it's accumulated a shift that is about 45 seconds since the discovery. So it's very tiny, but a little shift in the orbit means that then when you try to demodulate the pulsation, you'll just get it wrong, and you can measure it extremely well. So this was the first evidence for gravitational waves, back in the late 70s, much earlier than the actual discovery of gravitational waves by LIGO a couple of years ago. The sort of poster child for binary physics of pulsars with to test gravity is the double pulsar. So in this system, both neutron stars are both emitting pulsed emission that are visible from Earth. So there's a 23 millisecond pulsar and a 2.8 second pulsar. So it's really nice because then you can measure independently the orbit for each of them. And then you measure more, of these parameters, that can constrain the masses in the system, but also then these extra parameters that you measure, they each become a test of general relativity or whatever theory of gravity that you have. So in this system, we can basically measure 6, post-Keplerian parameters. And these parameters, basically, they constrain the masses to be extremely accurate, down to basically a thousandth of a solar mass, for both pulsars. And actually, Michael Kramer and colleagues have just submitted a paper where they update the timing of the double pulsar. And now it's I think 2 orders of magnitude more accurate. So you can expect a paper on the archive hopefully soon that, where you have even better measurement. But back from 2006, by using the best measurements of the post-Keplerian parameter, we could, which was the Shapiro delay, you can basically you can infer a measurement to about 0.05% accuracy of general relativity, compared to the prediction. So this is the best test of gravity in the what we call the strong field regime. There's a lot more you can do with pulsars to constrain gravity. For instance, if they have a white dwarf as a companion star, then the orbit tends to be also measured very accurately. And in this particular system, 1738, the orbit is not too long, and the orbit is also decaying over time due to potentially gravitational waves. But because you have a white dwarf, in this case, you can actually use optical data, optical spectroscopy, for instance, to directly measure the mass of the white dwarf. So we have, nowadays we have extremely accurate models for the white dwarf spectrum, where you can measure directly the surface gravity of the white dwarf by fitting the Balmer lines in the optical. And then you can do a dynamical measurement of the velocity of the white dwarf around the pulsar. So by taking the ratio of the velocity of the pulsar to that of the white dwarf, you can directly measure the mass ratio in the system. So this is Q. So on this plot here on the right-hand side, you have the mass of the white dwarf versus the mass of the pulsar. Then you can measure the mass of the white dwarf basically directly from the fitting of the spectroscopy. And then this is the observed change in the orbital period over time that you measure, and it draws like, this sort of curve. And so then you have essentially 4 constraints on this mass-mass diagram, which means, 3 constraints, which means that you can use the 2 best measured one, Q and MC, as like, your anchor point, and then the orbital decay can serve as a test for relativity. Okay. And it's really interesting because then you can start doing, tests of the strong equivalence principle. The SCP, in relativity says that the gravitational mass is the same as the inertial mass. So basically, what matter is made of should not affect how gravity behaves. But other theories of gravity, like scalar tensor gravity theories, would predict that the amount of gravity that a certain baryon, a certain mass induces is different from its inertial mass. And usually this will lead to things like slight polarization of the orbit or violation of the strong equivalence principle. So according to GR, for instance, gravitational waves are purely a quadrupolar type of wave. But if SCP is violated, you could get dipolar gravitational waves, for instance. So the excess, so if you take the measurement of the orbital decay and you take away the part, that is predicted by general relativity, right? From the previous, example, you measure the masses, so you can predict exactly what the amount of orbital decay you should be getting, and then you subtract it from the observed data. Then the remainder, right, the excess should be equal to a number of terms. It could be caused by mass loss from the system. It could be caused by tides in the system, or dipolar gravitational waves, or a change in the gravitational constant. Okay, because you have very compact objects, you can basically rule out that mass loss and tides would have a very important effect. Okay, so these two should be very negligible. So it means that in this system, the excess of orbital decay should give you a joint constraint on the dipolar gravitational waves and the change of the gravitational constant. Okay, and this is what is displayed here on this plot. And GR predicts that both of these should be 0. So it should be 0, and then that's the 1 sigma and the 3 sigma contour, and basically the measurements agree with general relativity's prediction. So if you keep doing this experiment over time, you expect this should improve. And maybe one day we'll see that, GR, might no longer be, the right theory. But so far it has passed, the test that we've made. There was also a triple system that was discovered a few years ago. So in this case, you have pulsar where a white dwarf is orbiting in a fairly tight orbit. So the orbit is about 1.6 days, okay? And the companion white dwarf is 0.2 solar mass. And then much further out in an orbit that's about a year is another white dwarf that orbits. So we call this a hierarchical system because triple systems tend to be quite unstable, but if you have an inner pair that is quite compact, then for the outer one, it looks more, the third object, it looks more or less as if like there's a point mass, near the center. And so it's a system that is fairly stable dynamically. Nevertheless, we can time all of, the motion of the pulsar very accurately. And you need basically to solve the three-body problem in order to, account for the Doppler shift over time. And so the motion is quite, complex. You can only obviously solve the three-body system numerically. And so you can see the orbit of the pulsar kind of like jiggling around a little bit. So the overall like circle here is due to the, the inner white dwarf, but then the little jiggling is caused by the outer, the outer star. And then if you evolve it over time, then you can actually, account for the orbit. But the nice thing is that you have two white dwarfs that have very different masses in this system. So the amount of gravitational binding energy between the two white dwarfs is very different. So if there is such thing as a SCP violation, then the amount of gravitational pull from each white dwarf will be different, not only because they're different mass, that goes without saying, but actually an alternative theory to GR would predict that there would be extra gravity or a bit less gravity, basically depending on the mass, depending on the on the binding energy of the object. And the measurements that have been made basically agree again with GR, so no SCP violation. And the reason why it's important to do these measurements is that you can basically cast most families of gravity in sort of like a tensor scalar parameterization, where A is the tensor field and alpha is a tensor field and beta is like a first, a linear vector field. And you can find basically, in the solar system, you can find regions where of this parameter space where the test of gravity will not violate SCP, but where in a strong field regime, SCP could be violated, okay? And it all has to do essentially with the self-binding energy of the different objects. So, relativity is this sort of, and gravity are this, strange thing where, depending on how you test it, you can get different results. And so it doesn't mean that, if some test of gravity passes very accurately the test in solar system, that it would not be violated in the self, in the high self-binding energy of neutron stars, for instance. Okay, so for the next few minutes, I want to move on to the neutron star equation of state. So neutron stars are very fascinating objects because they really have properties that we can't reproduce on Earth. So if you think of like the parameter space, the phase space of like the state of matter, right? In sort of like everyday life, we have matter that can be, solid, liquid or gaseous, right? But then at, but that would be very low temperature and essentially very low chemical potential, or essentially low like velocity, if you want, or very low pressure rather. Okay, so low pressure is like, pressure is kind of like chemical potential basically in terms of thermodynamics quantities, and then temperature or velocity, right, or like essentially the same thing. So real life is basically at the very corner here, right? Very low temperature and very low pressures. But then when you look at like the full phase space, then there's a lot of, that is basically unexplored. with things like LHC, you can probe collisions, right, of ions at really high velocities. So basically high, kinetic temperatures, but the pressure is very low, right? Because you're talking about just a few particles that, collide. Whereas in neutron stars, the temperature, even though in a neutron star, the temperature can be, millions of degrees, it's still essentially low temperature compared to like heavy ion collisions. But then in neutron stars, the gravity is such that the pressure is large, and then you have high chemical potentials. So what you can test in terms of phase space is very different in neutron stars. Now, this relates to the bulk property of the star, because how dense matter is and how it behaves is connected to what we call the equation of state, right? So for regular matter, we know of the ideal gas equation of state, but at higher density or higher temperature, then the equation of state will change. And so this brings us to Tolman, Oppenheimer, Volkoff, who all basically derive what is the stellar structure equation, but from general relativity. So you basically use the essentially the Schwarzschild metric, but then you solve it for a case where you're not considering just the outside solution to the GR equations, but where you are inside an object where the pressure will change as a function of mass. And so the solution is valid for a non-rotating spherically symmetric body, which is also in essentially static equilibrium. And this is basically the TOV equation is basically the GR extension to the Newtonian case for stellar structure. So if you've done basic stellar structure, you would have seen the hydrostatic equilibrium. So essentially how the gradient of the pressure in an object varies, and it depends on how the density changes as a function of radius, but also how the mass changes as a function of radius. And you need a second equation to basically solve, which is the mass conservation, right? So it's how the mass varies as a function of radius. But then there's one more unknown, which is the equation of state. So if you put an equation that gives you how the mass changes of an equation that links the pressure and the density, right? These two equations, then you can fully solve for the structure of your object. Now, the TOV equation is basically an extension of this by solving the full GR equations. And this parameterization that you see here of the TOV equation is quite handy. So the first thing is that in GR, the mass conservation remains the same. So it's still dmdr is 4 pi r squared rho of r, but then it's the pressure as a function of radius that changes. So the first term is basically what we're used to in Newtonian case. Epsilon is the pressure, is the energy density. So it's basically the pressure, the density rho times c squared. Okay, so the two are basically the same, up to a c square factor. But then you have like a set of corrections, these two, which are special relativistic corrections, essentially, from time dilation and from contraction of lengths, more or less. And then the last term is the general relativistic correction that's due to the curvature of space-time. And so with these, if you specify an equation of state, again, like essentially a function of pressure and density, then you can solve for these and you can describe your object. So in the original paper, Oppenheimer and Volkoff did that, and they basically speculated that a good choice for the equation of state would be a polytrope. So basically the pressure is proportional to the density or the energy density of the object to some exponent gamma. And if you take a fully degenerate object, like a relativistic case, the gamma exponent should be 4/3, And in the non-relativistic case of, then you would have a 4/3 exponent. So if you do that and you consider the relativistic case, you end up essentially solving these equations, and you find that the maximum mass you could get for a neutron star, a star made of neutrons that are relativistic, would be 3/4, more or less 3/4 of a solar mass. Beyond that, there is no solution. So this means that the object becomes unstable and should turn into a black hole. We know, obviously, these days that there are neutron stars that are more massive than 0.7 or so solar mass. So obviously, this was wrong. And the reason why it's wrong is because the equation of state of neutron stars is much more complex than a simple polytrope that applies from the center all the way to the outside. So the modern versions of equation of states, they basically tend to be a mixture of different polytropes. Okay, so you can think of like different regions in the neutron star to be different types of polytropes. And the way that the various parameters are set are constrained by essentially the nuclear physics, of like at high pressure. So things like the symmetry exchange energy, the parity exchange in energy, and such will essentially change as a function of pressure and will make the equation of state be like various components as a function of mass shell. Now we can actually try and test what the equation of state should be, because a given equation of state for a given radius should predict a certain mass for the object. So basically, in a mass radius phase space, you would expect to find a certain curve for a given equation of state. And so on this plot, you can see a lot of lines. They're basically for all kinds of equation of states, because obviously we don't know which one is the right one. So there are equation of states that we call stiff equation of state, where basically there's not much change in radius as a function of mass. And there are some that we call the soft equation of state, where the mass changes a bit more as a function of radius, like these ones there. You can see that they all have an endpoint, and the endpoint is basically the maximum mass that the various equation of state predicts. So if you can find, for instance, a very heavy neutron star, you can basically rule out, different equation of states. So measuring masses for neutron stars is a good way to constrain the equation of state. And already with the mass measurements, you can see a couple ones listed there. We can actually fairly confidently exclude a big bunch of neutron stars equation of state that cannot reach, the likes of 2 solar masses or so, where the most accurate measurements have been made so far. There's also speculations that maybe pure quark stars could exist, and could be in some cases what we think are pulsars or neutron stars. And those, they tend to have like these like funky like types of curves. And those don't seem also to match observations. So the equation of state is really how matter behaves inside the neutron star, and that is vastly unexplored. Overall, we think that neutron stars have like an atmosphere, which is like very thin, something like maybe a centimeter thick, that contains, like particles, like more like normal gas. Over time, this should be, because the neutron star sits on the interstellar medium, it should accrete very slowly some of the matter from the interstellar medium. So you would expect maybe the little atmosphere of a neutron star to be fairly hydrogen rich. And then underneath is the crust, where basically as you go deeper and deeper in the crust, then the high pressure would mean that electrons and protons would tend to combine and form neutron, via the inverse beta process. And so you expect that as you go deeper in the neutron star, the fractional mass of neutrons would increase. And then at some point you reach the core of the neutron star, where essentially it's quite a mystery what happens there. The neutron star could have a core that is more or less like standard matter, mostly pure neutron sort of lattice, but it's not quite clear that this is the case because our understanding of the equation of state at high pressure is very poor. So people speculate that it could be kaon condensates or pion condensates or other exotic materials, or maybe even that regular hadrons would actually break apart and you would have a quark gluon plasma at the very center of neutron stars. So which one of these we don't know, and that's what we're trying to do when we probe the equation of state of neutron stars, for instance by measuring masses. So I'll just skip over the details of which, but we can measure masses for neutron stars fairly well for the pulsars that are in binary systems, either because we observe the relativistic effects like I described earlier, or because we have optical observations, for instance, of the companion star. There's another way you can probe the equation of state of neutron stars, and it's via the cooling. So a neutron star should cool down over time, just because you essentially have a big thermos, right? You have a big bulk of matter that is hot, and eventually it loses energy. Some of it through photons, but especially for young neutron star, it tends to be the ERCA process that dominates. So basically, it's cooling via neutrino emission. And so young neutron stars, especially the younger they are, the faster they should cool down. We talked a bit earlier about the lack of very young neutron stars. So we know of a handful of neutron stars that are only a few hundred years old. One of the youngest ones is Cassiopeia A, so in the center of the supernova remnant of the same name. This star was observed to explode about 330 years ago. And there's I don't know which one of the dots there, but one of the dots basically is an X-ray, a bright X-ray source, which sits right at the center of the remnant, and it's a neutron star. But so far, all searches for pulsations from it have, remained, unsuccessful. So it could be that, it's a pulsar, but it's not beaming towards us. We just don't know. But we see the thermal emission basically from the surface of that object. Now, to first order, the X-ray spectrum. So you see the spectrum with like two different data sets from different observations. And to first order, the spectrum basically looks like a black body, right? So you have a very hot object and it cools down over time, and it's basically black body emission. But a bit like regular stars, which, in a very rough way, a star like the sun has a spectrum that looks like a black body. When you look in the details, then it's a modified black body because you have like absorption lines and whatnot. So in the X-rays, it's the same thing. And then comes, the modeling of the atmosphere of the object to then account, for the observed spectrum. And a big breakthrough was done about 10 years ago when Ho and Anke essentially found that the atmosphere of Cas A actually fits much better a model where you have a carbon atmosphere that has a low magnetization. And so it's presumably because this is a very young neutron star that still has like essentially some sort of fusion on the surface, and not much mass has been accreted. The other thing is that over the time for which we've got nice Chandra observations, you can basically measure what the temperature of the star is, and we see that the star is cooling down, and we have a rate for the cool down. And so the model basically depends on the equation of state of the star, as a bulk property. So the mass and the radius, if you change how compact it is, then the star will cool down faster or slower. So you can basically constrain, and these are the constraints on the mass and radius of the neutron star. You can also, there were other measurements done recently from what are called like accreting neutron stars that are essentially in quiescence and cool down very, like re-radiate the accumulated energy from accretion. And these are like these dotted lines there. So we're starting, with X-ray observations, we're starting to constrain the equation of state quite well. And that's basically it, for the equation of state. Now I've been talking for a while, and I could talk for a lot longer, obviously, but I think I should probably stop here. I just want to mention maybe one more thing. So there's a few slides I haven't talked about. I wanted to talk a bit about binary evolution, but I'm not. I think it's probably something that is less interesting to you folks. But perhaps you should just know that the binary systems containing a pulsar are basically systems that in the past contained a star, right, that evolved in a giant and transferred mass onto the neutron star through an accretion disk. And these we know as X-ray binaries. So the pulsar that we observe now are basically really old X-ray binaries that have stopped transferring mass onto the neutron star and are now like in this sort of permanent state of quiescence with no accretion disk. So this is the classic picture of binary pulsar evolution. You have a star that makes the neutron star accrete and then spin really fast by conservation of angular momentum, that is transferred. But about 2009, a pulsar was found in a system that used to be an X-ray binary 10 years earlier. And then in the same system actually disappeared around 2014. And the system now has an accretion disk again. So it's really sort of like completed like our picture of like the binary evolution, which is that this X-ray binary turning into a radio pulsar is now turning back in an X-ray binary. And we think that the picture of evolution is more messy than that. Basically these systems, they go through these phases of accretion and non-accretion for quite a while. So this system is called 1023, and I won't give too much these details about all of that, but two more sources, one in the globular cluster M28 and another one in the galactic field that's called Pulsar J1227 have been seen to switch between being a radio pulsar and being an X-ray binary, basically. So it really links the binary evolution, and it's massively interesting, to be able to follow the evolution of binary systems and their accretion disk. Right, so that's it. So I'll leave you with this this like funny whiteboard from where basically people were laughing about neutron stars because they seem to be able to do everything for physics, testing gravity, testing equation of states, and whatnot. And yeah, I'll take a few questions if you have any.
Okay, thanks a lot, Rene. So yes, let's go.
Thanks.
Okay, if people want to put their hands up online or here,
I have a question. Yeah, so could you go back to the slide with all these equation of state for nuclear stars?
Yeah, just a moment. Right here, this one.
Yeah, so could you explain a bit more? What do these gray-shaded areas?
Yeah, of course. Yeah, so some of the sort of easiest constraints for the equation of state are basically from centrifugal force, right? So if you have a rotating body, right, then comes a point where, given its radius, the gravitational force would be smaller than the centrifugal force, and the object should just break apart. So we call it a breakup limit, and so that limit can be probed basically by fast spinning pulsars. And so the fastest spinning pulsar that we know of is this pulsar here that has a 716 hertz rotation frequency, or 1.399 milliseconds spin period. So it's a pulsar that's in the globular cluster Terzen 5. So it's called TER5A because AD because it's essentially the like the 30F pulsar that was found in that globular cluster. And so just from the rotation of that pulsar, you can set essentially a limit on the mass and the radius this way. So if it's below in that gray area, the object will fly apart, basically. And then there's another region, and it's just for show, because we still haven't found a pulsar that is faster than 7 and 16 hertz. But if you were to find, a 1 kilohertz pulsar, this would be the region, right, that would be impossible. And that's completely model independent. It's purely from rotation, that you can set a mass radius constraint. So obviously, searching for pulsars can be also very useful, because if one day we find an extremely fast rotator, we could rule out also a bunch more of the equation of state for them. Then the mass, like I said, the total mass of the neutron star can be used to rule some of the equation of states. Then there's also what's called a causality limit. So at really high density, so at the top left corner, right, you can imagine a state where basically, given a mass, the radius is so small that you have a black hole, right? So that's no longer a neutron star, obviously. So this is this limit. But even before getting there, there's a region of the parameter space where the speed of sound would be faster than the speed of light in the object. And that is also not possible, because then the object would not be causal, right? So something could happen somewhere that the rest of the star essentially, would not know about, from the speed of sound being, faster than the, essentially you could knock, if you were to go with a hammer or whatever, you can knock one side of the neutron star, right? And then the other side would know of it, right? Because of the speed of sound propagating the pressure, but that would happen faster than the speed of light. And this is not possible according to GR. So this is the region that's here, basically. Yeah.
Yeah, and I'm sure we'll have more people talking about this diagram in lectures in the rest of the course. But
yeah.
Okay. Well, maybe people want to eat lunch, but yeah, it's thanks a lot for this introduction. I think you've done a very good job covering almost everything.
Yeah.
I hope this was worthwhile. Yeah, thanks, and we'll continue tomorrow with more on detailed electromagnetic signatures, like observations of neutron cells. So yeah, thanks everyone.
Great.